Okay, now we are going to get to defining the derivative, the heart of calculus. Calculus is all about limits, and the most important limit we have is the derivative. And the derivative is related to the average rate of change. So average rate of change would tell me the slope of a secant line connecting 2 points. So I have some function here, and I've got these points at x equals a and at x equals x. And then just change in y over change in x would tell me the slope of this orange line here. The derivative is when we let these points get closer and closer and closer together until they just become one single point. And instead of a secant line, when these points get closer and closer together, we eventually get a tangent line that maybe would come through like this and just kisses the graph, just touches it, and is parallel to the graph right at that one single point. And that happens when we make these points get closer and closer together. So we'll call this point here A, that's x equals A, and then my change in x here, we're going to call H. So if this is A and I go up by a different distance H, this next x value would be x plus H. So these 2 points are A, comma, F of A plus H, comma, F of A plus H. Then just change in Y over change in X I named H. And then what we'll do next is take the limit as delta X, this distance, H, goes to 0, and we get the derivative. Now, alternatively, we could just say, oh, we got 2 points, X and A, and I'll write my average rate of change like this, and then I'll take the limit as X approaches A. So we'll have 2 different ways of writing up the derivative. They're completely equivalent. I prefer this way, but we'll do some both ways. Okay, so we can see here, I've got some secant lines. I'm letting this point, I'm keeping this point fixed, and I'm letting this point move closer and closer. I'm taking smaller and smaller H values. I'm letting X approach A. Then these lines that we're graphing, these secant lines, get closer and closer to a tangent line. Then that would tell me an instantaneous rate of change. Average rate of change is you drive from here to Tampa, it's 100 miles, and it takes you 2 hours. What was your average speed? Well, you did 100 miles in 2 hours. Your average speed was 50 miles an hour. That's an average velocity. Instantaneous velocity is how fast are you driving right now at this moment. You weren't driving to Tampa at 50 miles an hour the whole time. You were going 70, and then you got down by Disney, and all the tourists were blocking traffic, and you went down to 20 for a few miles, and then you got back up to speed. So the derivative tells us your instantaneous rate of change. How fast are you going at 6 p.m.? And we do that by taking a limit. Okay. So you'll want this written down someplace in your notes. 2 different ways to define the derivative. These are equivalent. I prefer this one, but just for fun, we'll do a couple problems like this as well. We take the limit as X approaches A of just changing Y over change in X. Or equivalently, we call that change in X there. We just name that H. And that's the same as taking the limit as H approaches 0 of f of x plus a minus f of a plus h minus f of a over h. Okay, so let's find the slope of a secant line here. That's an average rate of change. That would be change in y minus change in x over, or change in y over change in x. So I need to find both of those y values. F of 13 would be square root of 4, that's 2. F of 10 would be square root of 1, that's 1. So change in y, 2 minus 1, over change in x. I got to make sure I get these matched up. That y value went with that x value. That y value went with that x value. What do we get? 1/3. That would be an average speed. Later on, we'll figure out how to find instantaneous rates of change. Okay, so let's take this guy here and find the derivative, the slope of the tangent line at x equals 3, using both different definitions, just so you can see you get the same answer. So if we look at the graph, oh, it missed there. We're talking about right here at that point. Let me change the color on my marker here. I'll do orange since that's what they were doing. My secant line would kind of look something like this. You can see he's got a pretty good slope there. That's what we're finding. In both of these, we're finding the slope of that orange line right there. Okay, so this limit here, the slope of the tangent line, is the limit as x approaches a. Well, I know a is 3, so let's put that in. Of f of x, I know what f of x is, it's x squared. Minus f of a. So now I'm literally plugging 3 into x squared. That's 3 squared divided by x minus 3. Now remember, when you're finding a limit, first thing you think to try is, well, let's just plug it in and see what happens. Anytime somebody asks you to find a limit, that's the first thing you're going to try is just plug it in and see what happens. And you could try that if you wanted. If I plug in 3, I'm going to get 9 minus 9, 0, over 3 minus 3. I get 0 over 0. Anytime you get 0 over 0, that means you're going to be able to factor. And with these derivatives, every single time, that's what's going to happen. You're going to factor something and cancel something. So let's do that. Notice I'm going to write limit at every step until I actually take the limit. That's a place people lose a point quite often. You have to write limit at every step until you take the limit. So I factored, hey, this thing that was causing the problem that gave me 0 over 0 cancels out. So I get the limit as x approaches 3 of x plus 3. Now that that offending guy has canceled out, I try again. Let's plug it in. Let's see what happens. Now I'm actually taking the limit. Once you plug it in, you don't write limit anymore. You've done the limit. 3 plus 3, I'll write it out, is 6. Notice I had to write limit everywhere here, but then once I plugged in, that's when I stopped writing limit. This is the only correct way to write this up. So I got 6. So what I'm claiming is the slope of that tangent line right there is 6. Okay, let's play the same game here using the other version of the definition. These are equivalent. So I'm claiming the slope of the tangent line is the limit as h approaches 0. H is just change in x of f of a plus h. So maybe as side work, let's write this out over here. This is not part of my answer. F of x is x squared. So I'm just going to write some stuff down. This is just to help you visualize what's going on. A lot of mistakes happen with function notation. If I wanted f of 13, what would that be? That would be 13 squared. If I wanted f of negative 35, that would be in parentheses negative 35 squared. If I wanted f of triangle, that would be in parentheses triangle squared. Whatever is sitting here, no matter what it looks like, is going to replace that x right there. So f of x plus h, f of a plus h, plugging into this function would be a plus h squared. I can't emphasize this enough. That moment that just happened is the most important moment of the entire semester. If you're confused by what's written down here, pause this video, rewind it, watch it over and over again. I can't put enough emphasis on this. If you don't understand what I've written right here, you will not make it through calculus. And I am taking this function that they handed me, and every place I see an x, I'm replacing that x with an a plus h in parentheses. Because that's what this right here is telling me to do. So let me write that down. So that's just this. A difference quotient has three different pieces. You got that piece right there, number one. That's what I found right there. Minus. I'm supposed to subtract from that f of a. Well, what is f of x? X squared. So f of a would be a squared. We'll call that part number 2. And then that whole thing is over h. So difference quotient has 3 separate pieces. We write them down separately, and that's just simplifying. Okay, now we know what h or what a is, so let's go ahead and put in a. My a value here, now I'm going to write it up here so it's clear when everybody's looking at this document. A is 3. Okay, number one mistake made in a college algebra class is about to happen right here. You guys are in calculus and you should not be making this mistake, but it still happens. You cannot distribute a square over addition. I'm going to erase this in a second, but very common mistake here. People will do this. They'll just distribute, just square them both. You cannot distribute a square over addition or subtraction. They call that the freshman dream. Like it has its own Wikipedia page. Because it's such a common mistake. Now, what's it mean to square something? Squaring something means multiplying it by itself. So I'm still going to write limit as h goes to 0 at every step. I'm going to write this out. 3 plus h times itself. That's what it means to square something. I'll go ahead and do that. 3 squared is 9. And now I got a FOIL. Notice I'm writing limit as h goes to 0 at every step. So what do we get? We get 9 plus 3h plus another 3h. So plus 6h. And then last. First, outer, inner, last. I'm just foiling. Minus 9 all over h. Hey, has anything pretty happened? Oh, the 9s cancel. Try to not catch that H there. Let's see if that works. Yeah. Okay, so the 9's canceled. Let's write down everything that's left. Limit as H approaches 0. I've got a 6H plus H squared over H. On the top, everything has an H in it. If you get to this point and something on top doesn't have an H in it, you've done goofed. So at this step, what we're going to do is factor out the H. You cannot cancel these H's right here. Another common mistake. These H's do not cancel. Only factors cancel, which means you have to factor top and bottom. So I would like to keep going straight down, but I've run out of room. I'm going to come across. Factor an H out of the top. So you should check yourself that that is factored correctly. Oh, look what happens. The H's are going to cancel. That's going to happen every single time. Remember, when you're asked to find a limit, what you would like to do is just plug in the value. I would like to just plug in H equals 0. But then what would I get? If H equals 0, I get 9 minus 9, 0 over 0. But now that I've canceled the H's out, now I can plug in H equals 0. So now I'm actually taking the limit. I'm not going to write limit anymore. 6 plus 0 equals 6. That's it. That's the slope of the tangent line at x equals 3, at the point 3, 9. And either definition gets you there. Okay. We call this the derivative at that point. So we just found the derivative of f of x equals x squared at x equals 3. And you should write this down in your notes. You should have that in your notes, but you're going to be doing so much of this. You're going to have this guy memorized pretty soon. That's a good place to stop for this video.